4, 3, 2, 1, and booster ignition, liftoff of Space Shuttle Discovery.
There is a change associated with almost everything around you, like change in the velocity of the rocket. There is a daily change in the temperature in your room, and there is a change in the expansion rate of the universe. To express this change in a mathematical language, we use the framework of calculus. Calculus provides a way to construct quantitative models of change and deduce their consequences. The development of calculus and its application to physics could be the most significant factor in the development of modern science. We will have a preliminary review of calculus for its applications in physics. In simplest terms, a function is an ordered pair of numbers with property that the first members of pairs are all different from one another. An example of function is 1, 1, 2, 3, 3, 1. An example which is not a function is 1, 1, 1, 2 and 3, 2. This is not a function because the first member of pairs, in this case 1, is same for two entries. Generally, functions are named as f, g or h. If we call the above function as f, it is described as f of 1 equals 1, f of 2 equals 3 and f of 3 equals 1. The first member of pairs are called arguments, while the second members are called values. Also, the whole set of first members are called domains of the function, and the whole set of second members are called the range of the function. Usually, to represent functions, we don't write the whole list of tuples as we did earlier. Instead, we represent them in variables. An example is the identity function f of x equals x, where x belongs to integers. If x lies between 0 and 5, the tuple representation of function is 1, 1, 2, 2, 3, 3, and 4, 4, and 5, 5. If we allow x to take real numbers, then we can also plot it in a graph. On a two-dimensional plot, we label the x-axis as x and y-axis as the function of x. Now, for the values in the domain of x, mark the corresponding values for f of x. In this case, we find a straight line passing through the origin. This plot represents f of x equals x. Similarly, we can have more complicated functions. F of x equals x square, f of x equals x square minus 7x plus 5, f of x equals x cube minus 5x, f of x equals exponential of x, and f of x equals log of x, and so on. The functions of the form which are represented as f of x equals mx plus c are called linear functions, where m and c are numbers. M is called the slope of the line and c is called the y-intercept. Let's just focus on the slope. The slope tells us how steep the line is with respect to the positive x-axis. If the slope is 0, then line is flat along the x-axis. If the slope equals 0.1, line is a little bit steep. If the slope is 10, then the line is quite steep. If the slope is infinity, then the line is perpendicular to the x-axis and parallel to the y-axis. The slope can also be negative. It only means that the line is slanted in the opposite direction. The value of slope is given by the tangent of the angle made by the line with the positive x-axis. So m equals tan of theta. If we plot the quadratic function f of x equals x square, we do not get a straight line, we get a curve. We can also see that the slope of the curve is not constant, it changes. The slope for smaller values of x is small and slope for larger value of x is large. This slope of function at x is called the derivative of function at x. It is represented as f dash of x or df by dx. So whenever you want to measure the slope of a function at a point, Evaluate the derivative of the function at that point. Derivatives have three simple properties. First is the derivative of addition of functions is the addition of derivative of individual functions. Second property is the product rule. The derivative of f into g equals f into derivative of g plus g into derivative of x. And the third property is that the derivative of a constant is 0. If you want to take derivative of a polynomial, then use the properties of derivatives along with the formula that derivative of x raised to n equals n into x raised to n minus 1, where n is a real number. Another formula is the derivative of sin x is cos x. To see this graphically, plot the function sin x. We see that the slope of sin x at x equals 0 is 1. The slope at x equals pi by 2 is 0. The slope at x equals pi is minus 1. The slope at x equals 3 pi by 2 is 0. And the slope at x equals 2 pi is 1. If we join all these values of slopes, we get the graph of cos x. Thus the derivative of sin x is cos x. Similarly, the derivative of cos x equals minus sin x, and the derivative of exponential of x equals exponential of x, and derivative of log of x equals 1 by x. If you have a function of a function, then you can take its derivative by using chain rule. So f of g of x is a function f of a function g of x. To give an example, let g of x equals x plus 1 and f of x equals x square plus 3. Then f of g of x equals x plus 1 the whole square plus 3. By using chain rule, the derivative of f of g of x with respect to x is given by the derivative of f with respect to g into the derivative of g with respect to x. In this case, the derivative of f with respect to g evaluates to 2g and the derivative of g with respect to x evaluates to 1. So the final answer is 2 into x plus 1. Another example is the derivative with respect to x of exponential of x square. Here f of x equals exponential of x and g of x equals x square. Then f of g of x equals e raised to g of x, which equals e raised to x square. In this case, df by dg equals e raised to g of x and dg by dx equals 2x. So the final answer is exponential of x square into 2x. Suppose you have given the position of a particle as a function of time, so x equals x of t, and asked what is the velocity of the particle at a time t equals to t0. Well, you know what to do. You have to take the derivative at t equals t0. That is, you have to draw a tangent at t equals t0 and measure its slope. So the derivative of the position with respect to time is velocity. Similarly, if you know the velocity, you can find the acceleration by taking the derivative of velocity with respect to time. So dv by dt is equal to a of t.